This is Lab 11, The Falling Slinky by Sarah Hojati, Lab Section M04. The presented question is, what happens when you drop a slinky? Will the top go to the bottom? Will the bottom go to the top? Will both ends move together and fall down? Or will both ends meet in the middle? So I use the momentum principle to model this motion and try to find the answer. There's a video made to show how the slinky is dropped, and I extracted this data using Tracker. So first I extracted the position of the top of the slinky as it moves down. The origin is where the professor lets go of the slinky at the beginning. And the video is calibrated to the length of the tennis ball, which was found to be 0.0635 meters. So this tracks the motion of the top of the slinky. And I also tracked the motion of the ball, which is relatively still throughout the video. I tracked both of these data and put it on Excel to compare them with the model. I modeled the same motion extracted from Tracker using VPython, and in order to do that, I took Lab 8 and right here, I took Lab 8 and with the spring motion, and I edited it to include the motion with the spring. I calculated the position of the spring using the momentum principle, and I then graphed the data of the spring and ball position. So if you run it, right here, you can see that as the top of the spring moves down, the bottom of the spring and the ball are relatively still until the top of the spring reaches the bottom when they move a little bit. So these two graphs right here show it models the position of the ball. As you can see in the first graph right here, the position of the ball is shown and the forces that are acting on the ball. So this force is the force of gravity and the force of the spring. And so as you can see, even though there is a force acting on the ball, there's no motion acting on the ball. And this graph right here shows the force of gravity and the force of the spring, and the blue line is both forces acting together. So as you can see, there is a force over time, but the ball still remains stationary. So right here, I have plotted the position of the ball. The blue line is the model and the orange line is the experimental. And they're different because the length of the spring was unknown, so I just had to use the length of the spring from the Lab 8. So as you can see in both cases, the ball remains stationary. Here is the position of the spring, and as you can see in both cases, the position of the spring decreases exponentially, but there is some difference because the spring constant, the spring mass, and the length of the slinky are all unknown. So the data from Lab 8 had to be used. So when I play the video, right, just like that, you can see that the ball is stationary until the top of the slinky reaches the bottom, and almost magically the bottom of the slinky doesn't move at all, and then when the top reaches the bottom, it seems to realize that the forces are unequal and move. So the explanation for this is that although the forces are unequal, it takes some time for that motion to propagate at the speed of sound to the bottom of the slinky, so that by the time that information gets to the bottom of the slinky almost, like I said, realizes that the forces are unequal, and it takes a small amount of time for that to happen. So that's why there is a delay in the difference in force and in the motion of the slinky. So thanks for watching.